Hello and welcome back. Here we start a new chapter on an element. And a whole chapter focused on just one element. So we're going to talk about organic chemistry and what is it? Why are we going to talk about it? What's important that makes it worth spending all that time for one element on the periodic table? We're going to draw things, which you've done before, Lewis structures and things like that. But it turns out in organic chemistry they have their own ways of drawing things that get a little more complicated, but are actually simplified. So once you get used to it, you really like this new method. When you're first learning it, you're like, why are you doing that? We're going to talk about isomers, all these different ways we can arrange the molecules, some of which do stereoisomerism and optical isomerism, which do this funny thing called rotating light. And we're going to talk about the rotating light in excruciating detail, but don't worry, the excruciating detail is optional, but the other parts of it aren't. Then the functional groups. Lastly, we're going to talk about these common groups that we see in chemistry. You're going to see them a lot if you take an organic chemistry class. And just kind of, this is your first introduction to them. We're just going to say, hey, can you recognize these major functional groups? Like if you see them walking down the street, be like, hey, how you doing, Esther? Good to see you. Apologies to anyone out there named Esther, but there's a group that we're going to study called Esther. Okay. All right. So, what is organic chemistry? Organic chemistry is very simple. It is the study of molecules primarily composed of C and H. Now, there's this old C and H pure cane sugar song. I'm not going to sing it for you. But it turns out, it says from Hawaii, but it turns out C and H doesn't even make any of their sugar in Hawaii anymore, so it's really sad. But anyway, carbon and hydrogen. Carbon and hydrogen. Why carbon? What is so important about carbon? That quite honestly, when you're a chemistry major, you're going to take a whole year of organic chemistry, 2 semesters, full year of organic chemistry for carbon, essentially. And then the rest of the periodic table, they call inorganic chemistry, right? It's just the non-organic chemistry. They can't even name it something useful, like something different, right? It's just that chemistry that's not organic chemistry. You take 1 semester in that. So 1 year for one element on the periodic table, 1 semester for every single other element on the periodic table. Sounds crazy, but that's how it generally goes. Why is that? What's so important about carbon? What does carbon make up? Oh, like life. Oh yeah, carbon-based life form. Plastics. Okay, so a lot of carbon chemistry in there. Fuels, a lot of carbon chemistry in there. Medicines, a lot of carbon chemistry in there. Okay, so yes, carbon does a lot of interesting chemistry, and there's all sorts of things we can do with it. We're only just talking a little bit about it. We're not actually going to do any carbon chemistry too much in this chapter. We're going to be identifying things more than doing some chemistry. We'll save that for your organic instructors. So the study of molecules primarily composed of carbon and hydrogen. Then we have these things called hydrocarbons, which are molecules made primarily of carbon and hydrogen. Doesn't mean they're made only of carbon and hydrogen, just primarily. A bunch of C's, a bunch of H's, maybe an N over here, an O over here, a Cl over here. So other things are possible in there, and we'll see that when we get to the functional groups, but primarily made up of carbon and hydrogen. So how do we draw all these things? Let's start with the simplest hydrocarbon there is, 1 carbon. And if it's composed of hydrogen and carbon, we know that it's got to have 4 hydrogens around it to make that carbon happy. And that's a theme we're going to see. Carbon, 4 valence electrons. How many bonds does it like to make? It likes to make 4 bonds. How many bonds does carbon always make? 4 bonds. If carbon's going to bond to something, what does it do? 4 bonds. The only times you're going to see exceptions to that are things like carbon monoxide. That's about it, folks. Other than that, carbon makes 4 bonds. Everywhere you go, it makes 4 bonds. Doesn't always attach to 4 things. Sometimes it attaches to 3 things, one with a double bond. Okay, so those bonds were really far apart. I meant to do that, but it totally that's not what my fingers did. All right, so 4 bonds. Carbon makes 4 bonds. How many bonds does carbon make? 4 bonds. All right, so carbon makes its 4 bonds there. If you know this guy, his formula is CH4, and we call him methane. That's your natural gas. That's what you burn if you turn on your stove and you've got a natural gas stove. I used to have a car that ran off of natural gas, and it was nice because natural gas was really cheap when gasoline was expensive. So methane, that A-N-E tells us we have what's called an alkane, which is carbons attached to each other with single bonds and then hydrogens elsewhere. So we're going to see that on the ending of all of our things that we're drawing. Great. So there's a Lewis structure on the left. And for the most part, if you're going to draw CH4, people are going to draw a Lewis structure, or they're just going to say, hey, here's the formula CH4. When you get to a couple carbons, how many bonds does carbon make? Oh, right, 4 bonds. Okay, we're going to put a bunch of hydrogens around there. How do we know how many hydrogens to put? Because we know that carbon always makes 4 bonds. So we're going to put enough hydrogens around there to make sure that carbon always makes 4 bonds. That's just what it does. So we put hydrogens around 3 on the left, 3 on the right to make carbon have a total of 4 bonds for each carbon. And we say, hey, our formula here is C2H6. And if you know what this one's called, it's called ethane. So eth tells us 2 in this case. And the ane tells us, hey, we've got a bunch of carbons single bonded to other carbons with some hydrogens around it. And that's our ane, the alkanes. Cool. So we go to the 3 carbons, 1, 2, 3, and then we start to add hydrogens around them. 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. And if you notice anything about what I just did, you'll notice it was a bit tedious. There's a lot of hydrogens to have to write, and we're only at 3 carbons. I mean, how many carbons are in DNA? It's just an incredibly large number. What are we going to do? Okay, well, we're going to see in just a little bit. So CH3 on the left, CH2 in the middle. Why only CH2 here? Why not CH3? Because carbon always makes 4 bonds. We already had 1 bond to another carbon here. We had 1 bond to another carbon here. So we only had room for 2 hydrogens. So we always got to count those 4 bonds because that's just what carbon does. All right, our formula here, C3H8. If you want a formula, this is going to be N and this is going to be 2N plus 2. I don't really like that formula because it only works for the alkanes, and when you put anything else on there, that formula all of a sudden doesn't work. I say we're going to start drawing structures of these things, and we're going to see, oh, here's how we can count hydrogens, here's how we can count carbons. But you know, some people like formulas. You can use it if you've got an alkane. All right, this one you might be a little more familiar with is butane. That's what you're going to get in a lighter. So in the lighters, there's these little butane molecules, which are C3H8, 3 carbons singly attached to each other with 8 hydrogens around it. So when we get to the next one, boy, by golly, this one's going to get a little tedious. All right, 1, 2, 2, I have to be careful about what I sing so I don't get a copyright violation and have my video taken down. Okay, so bunch of hydrogens around there. Gets a little tedious to write. This guy is C4H10, and if silly. Wow, I wish I could go back in time. Meth, eth, I don't know what I was thinking. Propane. That one's propane. This one's butane. I need more coffee. All right, propane is C3H8. Butane is C4H10. My apologies for that mistake. All right, so propane, butane, again, that ane telling us a bunch of carbons singly bonded to each other with hydrogens around it. I don't want to keep drawing those. Do you want to keep drawing those? Those are pretty tedious to draw, right? How can we make our life a little bit easier so we don't have to draw all of these Lewis structures with all these hydrogens? I mean, imagine when we get to decane. So many hydrogens to draw, it takes forever to do. So people have done different things. One, they call this the expanded structure. Right? It's the Lewis structure, essentially, and it's the one that's got the most detail to it. But how can we reduce that detail a little bit and still get information across? Well, one way people do it is by breaking these guys into little groups. And we say, hey, look, there's a little group over here, there's a group here, there's a group here, there's a group here. And let's just draw a formula that has just those groups in it. And so we say, oh, we've got CH3, CH2, CH2, and CH3. And this is what we call a condensed structure, or condensed formula, I should say. You can call it a condensed structure as well. And it just highlights the different groups. Now you'll notice the way I wrote it, I didn't draw lines in between there. Some people do, but most people don't. And so I say CH3CH2. Now, does that mean that my hydrogen is attached to that next carbon? No. No, not at all. We know hydrogen only makes 1 bond. And so how can it be a central atom between 2 carbons? Because it only makes 1 bond. Yes, you can go to the literature and find that they've forced hydrogen to do other funny things. But in reality, hydrogen makes 1 bond. All right. So we actually have carbon attached to carbon, even when we write it CH3, CH2. Important to keep in mind. So CH2, CH3, CH2, CH2, CH3. And then when you get really long alkanes, some people will even write this. They'll write CH3, CH2, 2CH3. And they'll say, hey, even if I got 7 of those, 10 of those, I can just write CH210. So you'll see people write that as well. Not too common, but you'll see it sometimes. What's by far most common, if you're trying to do these structures and you're trying to save yourself a little bit of time, is to draw it like this. And you say, hey, I'm going to draw what's called a skeletal formula. What's a skeletal formula? Well, skeletal often means minimal, right? You take a skeleton, it doesn't have any of the skin and muscles and all those kinds of things. It's a minimal structure of a creature that you're trying to reproduce. Skeletal structure formula is essentially a minimal formula of what you're trying to reproduce. And I'm going to draw it for you. You're going to look at it, and if you've never seen it before, you're going to be like, that's weird. I'm going to explain it, and then as we get used to using it, you're like, okay, I kind of like that. So what does the skeletal formula look like? It looks like ding, ding, ding. And that, my friends, that little beep, 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 is exactly the same thing to a chemist as that top one. Right? Exactly the same. No difference whatsoever to a chemist between this top one and what I drew down there. Like, how can that possibly be the case? How can that skeletal formula be the same as C4H10? Well, it turns out there's a few rules for drawing skeletal formulas. One, endpoints that are unlabeled, right? So I've got a bunch of endpoints here, are carbon. So I've got carbon 1, 2, 3, and 4. Okay, so that's the 4 carbons. I can kind of see that. But what we're missing is all the hydrogens. And what we do in a skeletal formula is we say, hey, look, I'm going to draw everything except hydrogen. But if you notice that there's some bonds missing, because how many bonds does carbon make? Right, 4 bonds. Always makes 4 bonds. How many bonds? 4 bonds. That's all it always makes. If you notice there's any bonds missing, those missing bonds are hydrogen. So if we look over here at our first carbon, we've drawn a bond between carbon and the next carbon. So there's 1 carbon there, or 1 bond there, but we are missing some other bonds. We're missing some other bonds. We're missing 3 bonds because that's only 1 bond. We need to make 4 bonds. So we've got 1 bond. We need 3 more bonds. So what we're going to say is those 3 bonds are all hydrogen. And so really what's down here is there's actually 3 hydrogens attached to this guy. We just don't draw them. Why? Because we kind of know that they're there. And if we don't draw them, we save ourselves a lot of time. So they're there, but we don't actually draw them. How about on this guy? On this guy, we've already got 2 bonds drawn, 1 and 2 sticking out of there. So there's 2 bonds unaccounted for. So guess what? There are 2 hydrogens on this one, 3 hydrogens on this one, 2 hydrogens on this one, 3 hydrogens on this one. Let's compare that to our Lewis structure up here. There are 3 hydrogens on this one. There are 2 hydrogens on this one. So it does. It looks pretty much exactly the same once you know the rules. The 2 main rules are unlabeled endpoints are carbon, and carbon always makes 4 bonds. If it's not making 4 bonds, the rest of those bonds are hydrogen. And this is a skeletal formula for butane. Pretty neat, pretty fast to draw, pretty much what 99% of all organic chemistry does. Now, there's a lot of flexibility in a skeletal formula. If I'm trying to really emphasize something, I can mix a skeletal formula with a condensed formula, and I can draw something that looks like that. And that's exactly the same as the orange one. That blue one is exactly the same as the orange one. You're like, how can it be? I've got all these endpoints, right? I've got 1, 2, 3, 4 endpoints, and you put that carbon there. So I've got 5 carbons now. But no, I don't. Because remember what the rule was is unlabeled endpoints are carbon with 4 bonds. Put the hydrogens in as you need them. But I labeled this endpoint, so it's no longer a carbon and what I label it. It just becomes what I label it. Now, in this case, I labeled it what it would have been if I didn't label it. So it's kind of confusing, but you'll see this as we go along. Don't get too confused yet. Okay, so I put the hydrogens there. So you see that there's a mix here of the condensed formula and the skeletal formula, and that's perfectly okay. Most of the time, we're going to focus on the skeletal formula, but occasionally you'll see these things where people mix them, and that's perfectly fine. All right, so we went to butane, and that was C4. Now let's go to the next one. And if you remember, what is something with 5? It's 5 sides, right? Pentagon. And so we're going to draw pentane. And we know it's going to be C5. If we use our little formula, it's going to be H12. Pentane. What I always do when I'm drawing these things, when I put my pen down, I count 1. And then as I start drawing, 2, 3, 4. I personally love to draw from down to up to down to up. Some people like to draw from up to down. It doesn't matter. So I'm going to draw 1, 2, 3, 4, 5. And there is pentane, right? It took me that fast to draw it. That's why we use these skeletal structures. It's because they're so efficient. Let's verify that this is C5H12. We've got 1, 2, 3, 4, 5 unlabeled things. So that's our 5 carbons. This guy only has 1 bond drawn. So what does he have? He has 3 undrawn bonds. This one has 2 undrawn, 2, 2, 3. If we add up 3 plus 2 plus 2 plus 2, I think I said one too many 2s, plus 3, you get 12. So we're good. We have C5H12 just like we expected to, and that is my pentane. Now here's a question you might be asking yourself. Why is he drawing it up, down, up, down, up, down? I'm going to give you 2 good reasons. One, because if I didn't, I'd draw... Okay, that should really speak for itself. The second is that these are carbons bonded to 4 things. How many carbons? 4 things, right? So, right, not always 4 things. In this case, it's 4 things. It's always 4 bonds, but sometimes there's a double bond or a triple bond. All right, so I'm bonded to 4 things, which makes it a tetrahedron. And what does a tetrahedron look like, right? If it looks like that. But then what is the next one? The next one also looks like a tetrahedron, so it looks like that. And the next one also looks like a tetrahedron, so it looks like that. And what do we have? We have a main part down here that looks up, down, up, down, up, down. And so that's why we draw them with these up, down, up, down, up, downs, is because they are tetrahedral in general. And so they do up, down, up, down, up, down. Now, what we're going to see later on is that there's lots of different ways of arranging these and making shapes and funny things so that it's not always exactly up, down, but we can still draw it that way if we're just trying to get across the concept of our molecule. So up, down, up, down, up, down works really, really well. It's very easy to draw one too many lines, one too few lines. So it's a good idea to check and just, count your lines when you're count your endpoints, I should say, not your lines so much. Count your endpoints when you're done, just to make sure you have the right number. And moving along, we can then draw C6. 1, 2, 3, 4, 5, 6. C6H14. 6-sided is a hexagon, so we get hexane here. C7. 1, 2, 3, 4, 5, 6, 7. C7H16. 7-sided is yeah, this one's a little harder. Heptagon, and so this is heptane. 1, 2, 3, 4, 5, 6, 7, 8. C8H18. This is octane. You've seen that before. That's your gasoline, right? So you go to the pump, you decide to buy 87, 89, 91 octane. You pay more, pay less, whatever you do. By the way, most people I know who know things about cars buy the lowest grade because your engine's designed for that. In other countries, the grades are different. When I lived in New Zealand, it was 91 and 93, or maybe even 95 were the grades. And that grade's just telling you the quantity, essentially the fraction in there, and I don't actually know what the math is between those numbers and the fraction, of things that are actually octanes, so things that contain carbon 8. And then we get to my favorite one, 1, 2, 3, 4, 5, 6, 7, 8, 9. This one's going to be C9H20, and this one's called nonane. Right? Did you know that a 9-sided figure was a nonagon? It just sounds silly, and so I love it. And our last one that we're going to worry about, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, C10H22, and that is decane. All right, so I do need you to know methane through decane, and you need to do better than me. You need to actually get ethane and propane and butane correctly, because I mixed up my propane and my butane when I first wrote it down. But propane is C3, butane C4. All right, so I do need you to know how to do those. We're going to be drawing a lot of skeletal structures. So you want to practice drawing skeletal structures. We're going to be drawing or doing a lot more of interpreting skeletal structures, and so we're going to do that. as we go along too. All right, so we just did the alkanes. That's what those are. Methane, ethane, propane, butane, pentane, I always do this, hexane, heptane, octane, nonane, and decane. Now, if we were going a little bit further into organic chemistry, we'd start to talk about how to name molecules where we've got isomers of that. If you remember isomers from the last chapter, we broke a bond, we move it around. We're going to talk a lot more about isomers in this chapter. So we talk about how to rename isomers of that when we've got little carbons sticking off of that big chain. But we're not going to do that in this class. All right. So what I want you to do with me at this point, and guess what, you're going to do it on your own in just a moment, is we're going to practice counting how many carbon atoms and how many hydrogen atoms are in the following molecule. Now you'll notice this molecule is a little bit different. I don't just have up, down, up, down, up, down in the middle. I've got things sticking off of it. But the rules are exactly the same, right? This thing sticking off of it, this is still an unlabeled endpoint. It's still carbon, right? But what does it have? It has 3 bonds already drawn, which means only 1 is missing. And this guy at the end is still carbon, but he's only got 1 bond drawn, so there's 3 things missing. All right, so let's figure out how do we count this guy up, and you can pause your video and try it ahead if you want. How do we count this guy up to figure out how many carbons there are? And it's pretty easy to figure out the carbons. You're just counting end points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't worry about the numbering. I was just numbering. This is not actually the numbering you'd be using if you were actually naming this molecule, but I just counted that there's 10. So I know this guy is going to be C10. And then I got to figure out how many hydrogens I have everywhere. How many hydrogens do I have? Well, I look at the end. There's 1 bond drawn from this guy, which means he's missing 3 bonds. Those are all going to be hydrogen. This guy, 2, 2, 2. This guy, just 1, right? I've got 3 bonds drawn. This one, 3, 3, 1, 2, 3. If you count that up, I've got 3 times 4 is 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. C10H22. Now, if you remember our formula, N and 2N plus 2, we get the same thing here. And so you're like, oh, see, you said that formula wasn't very useful. By golly, it's proven to be useful because I could have got this question right without doing any work. Okay. Given. But what happens if you turn this guy into a bromine? Then your formula doesn't work anymore. And you still need to know how to do this part where you're counting everything. Okay, so I encourage you to not use the formula to actually be able to count these things out. All right, your turn. We want to know how many hydrogen atoms are in the following structure. Go! Just got to start figuring it out, right? All these end ones all have 3, right? Because there's just 1 bond drawn from them. I can put 3, 3, 3, 3, 3. Right? What can I do here? 2, 1, 2, 1, 2. Is that it? So I've got 3 times 1, 2, 3, 4, 5. 3 times 5 is 15, 16, 17, 18, 19, 20, 21, 22, 23. That doesn't seem right. Why? Because I put a 2 there, not a 1 there. Okay, that guy was a 1. 2 mistakes in the same video. Okay, so that's a 1 there, folks. Why? Because there's 3 bonds drawn. I don't know why I wrote a 2 there, but it should be a 1. All right, so that's going to be 22. And look, it's C10H22 again, right? So yes, if you just have a bunch of singly bonded carbons and you don't have any rings or anything like that because rings screw you up, then yes, that formula of 2N plus 2 totally works. But it's also good to be able to count these things, as we will see. All right, rings. I just said rings screw things up. Okay, what is a ring, right? It's connected. So how are we going to connect a ring? We're going to make a ring of carbons. What's the smallest number of carbons I need to make a ring? Right? And maybe you came up with 2. That's not really a ring. But maybe you came up with 3, and you're like, that doesn't look like a ring. But right, if I go like that, it does look like a ring. Unlabeled endpoints are carbon. So I've got 3 carbons here. And that is a ring, and it's the smallest carbon ring. And how we tell someone it's a ring is we still count up how many carbons there are, right? Methane, ethane, propane, butane. And so we're going to call this propane. But to tell someone it's a ring, we're going to put the word cyclo in front. And that's all one word, cyclopropane. So cyclopropane. Now, what's the formula of cyclopropane? It's going to be C3. How many hydrogens? Well, here I've got 2 bonds drawn and 2 bonds undrawn. Same thing here, same thing here. So this is going to be C3H6. And notice how our 2n plus 2 rule doesn't work anymore. So it's really good to be able to interpret skeletal structures to figure out chemical formulas. Next one, cyclobutane. Right? It's exactly the same. Butane tells us 4, the cyclo tells us in the ring, and we could figure out the formula of this is C4H8 if we wanted to. I'm not going to do all of them. Right? We don't run across too many that are larger than 6, although you absolutely still do. This is going to be cyclopentane. And this is going to be cyclohexane. I stop there because, like I said, most of the things we're ever going to see are some sort of derivatives of cyclopentane or cyclohexane, maybe some double bonds, maybe there's a few double bonds, other things. But most of what we're going to see in organic chemistry is either 5-membered rings or 6-membered rings. You do see 4-membered rings and 3-membered rings. Definitely. I took a whole class in 4-membered rings. It really was. It was a whole class in chemistry of 4-membered rings. But not as common as the 5-membered rings or the 6-membered rings. So cyclopentane and cyclohexane. Where are you going to see these? Well, let's look at one example right now. What kind of rings are present in cholesterol? Right? Cholesterol is that stuff when you eat too many hamburgers and fries, collects in your arteries. What does it look like? It looks like this. And what do we see? Oh, look, there's a ring of 6. There's another ring of 6. There's a ring of 5. Right? So all sorts of things. Now, like I said, you see them modified with double bonds and other things. Here we've got it modified with an OH. Looks like a hydroxide group, but it's not because it's not charged. Right? Hydroxide is OH minus. So we see some other things modifying it here. We also see some use of this stereochemistry notation. Remember, those dashes mean they're going away from you. The other ones mean they're coming towards you. And people do that because it turns out there is some interesting chemistry that happens where when you make these kind of rings, you do end up either flipping it up or flipping it down. And you get different behavior depending on whether it's flipped up or down. So people do like to present that kind of stuff. So cool. What are we going to do next? We're going to talk a little bit about structural isomers. Now, if you remember isomers versus conformers. Conformers, we're just rotating a molecule kind of around itself. Isomers, we're actually breaking a bond, forming another bond somewhere. And so what we're going to look at is we're going to look at pentane. 1, 2, 3, 4, 5. Looks like that. It is, again, C5H12 if you count it. So what I'm going to do is I'm going to make an isomer of pentane. In order to make an isomer, I've got to break a bond and form it somewhere else. So I'm going to take this carbon and I'm going to attach it way over here to this guy. So let me draw this and that's all I have left. I only have 4 carbons left because I broke that last one off and I put it on this guy. And so I'm going to stick him on top there. One thing we'll learn as we go along is that when we make this first V, we never draw anything inside that V. Everything's always outside of that V, and that just comes from the tetrahedral arrangement. When you look at a tetrahedron, once you have that V, everything else appears on the other side of that V. All right, is this the same molecule? This one is also C5H12. It has the exact same chemical formula, but when we look at it, it is a different molecule. Because in this first one, we had a chain of 5 different carbons. And here, the best we can do is 1, 2, 3, 4. No matter how I count it, I can't make a chain bigger than 4 carbons. And so it's a different molecule. Right? This one on the top is actually a pentane molecule. The one on the bottom is going to be 2-methyl butane. My brain had to think about it. 2-methyl butane. So it's actually a butane molecule and will have different chemical properties. I can do this darn thing again. I can make another isomer where I take this one and I move this guy over here and make that. And I make what I like to call the X molecule. And let me go back to my blue. The X molecule looks like this. So right, I took off that last carbon, but I put one here and one here. That's the X molecule. Also has a C formula of C5H12. However, the longest chain I can make here is 1, 2, 3 carbons, no matter what I do, right? I can't do a path where I can do more than 3 carbons. And so this one is actually 2,2-dimethyl propane. And it's a very different molecule than our original pentane, even though it's got the exact same chemical formula. And so we find that in organic chemistry, there are a lot of structural isomers where you've got the exact same formula, but very different arrangements of the molecules, very different arrangement of the atoms, so that we do have different chemical properties, different drawings and structures that we do. So we have to be able to distinguish those from conformers, which is just where we've rotated it around. So I'm going to draw my pentane again here. That's my pentane again. What would a conformer look like in a skeletal drawing? A conformer in a skeletal drawing would be, I'm going to take this guy and I'm going to rotate it down like that. And what do I get? I get this guy's like that, but I'm going to draw that other part in green, and maybe it looks like that. So I took this guy up here and I just rotated it down and put it down here. If I count, I still have 1, 2, 3, 4, 5 in a row. I didn't break a bond and form a new bond, which is required for making an isomer, right? I just rotated around it. Is this a valid skeletal structure? It's not up, down, up, down, up, down. Absolutely. You can draw skeletal structures in very many weird ways. Most people don't, because the whole point of a skeletal structure is to simplify the presentation of a molecule. So most people will not intentionally make it complicated, but you could. Right? So that's a perfectly valid skeletal structure to draw of pentane. But you can see that I've just rotated around one of my bonds there. So this is a conformer, a rotation around a bond. So your turn. So which of the following are isomers? Now, turns out there's more than one set of isomers in here, but only one set that's in your possible answer. So don't get confused by like, hey, these are isomers too. Yeah. I just didn't list them. So of the possible answers there, look at these things. Which are isomers? The other ones are all conformers. So that would be a go. I see you. Oh, you're doing a good job. Working hard. All right. What did you come up with? Well, hopefully when you're trying to find isomers versus conformers, what you're doing is trying to see, hey, can I make the exact same chain that I did when it was flat? Hey, look, I've got a flat one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So Q, R, and T are all conformers of each other. They're just a rotation of the same molecule, but I didn't actually change anything. I didn't break a bond and make a new bond. But S, the longest chain, is 5. In order to change the chain length, I had to break a bond, move it around somewhere else. In fact, I had to break 2 bonds. I had to break a carbon-hydrogen bond and swap that over as well. So S is definitely isomers of all of the other ones. So any answer that contains S must be our answer. And so that would be B here, is that S and Q are isomers. All right. Structural isomers versus stereoisomers. Okay. Remember, this is what we learned in the transition metals, and we're just kind of going to review it now, and then we're going to get into gritty, more detail about the optical isomers and the stereoisomers in just a moment. Right? A structural isomer is what we were just talking about. We talk about pentane versus the 2-methylbutane. That is a structural isomer. Remember, the stereoisomer is I had carbon or something else, and I had 4 different things attached. A, B, C, D, and I do I used C again, and I didn't last time. I used D and E, but it's okay. You know what I mean. I've got 4 different things attached, right? And if I just swap one of them, right, I make a mirror image of it, then those 2 molecules are non-superimposable, okay? So I cannot put the one on the left on top of the one on the right and just kind of rotate it in just a way. It's a mirror image of it, and it's non-superimposable. So they call it a non-superimposable mirror image is how you figure out a stereoisomer. So I did rearrange things. I did have to break bonds and move them around, but it looks pretty much identical unless you know what you're looking for. Whereas this one, on the top, the structural isomers are generally a little more obvious because you're like, hey, my bonds changed here, and I can see that there's actually like different connectivity essentially between my things. So structural isomers are actually indicated by different connectivity, right? That carbon was attached at the end, now it's kind of attached in the middle, whereas the stereoisomers are indicative of same connectivity but different spatial arrangement. I just flopped that C and that D around and made a molecule that wasn't the same as my original molecule. The one thing I do want to practice a little bit more, and I forgot to have a slide for it, so I'm just going to go ahead and scroll down here. And we're going to practice just a little bit trying to find chemical formulas from skeletal structures. And here I'm going to start substituting things. So I'm going to start putting things on the end. Because remember, the rule that I told you is that as soon as I label it, it ceases to become carbon and becomes exactly what I labeled it. So I'm going to leave off that label for now. If I left off that label, I'd have something with 3 carbons, right? 1, 2, and 3. But as soon as I put a label on there, that last one ceases to be a carbon and just becomes a chlorine. And now this chlorine is attached to carbon number 2. If I drew a Lewis structure for it, it would be CH3 on the left, it would be CH2 here, and it would look something like that. Okay, this carbon number 2 is attached directly to that chlorine. There's no hydrogen on the chlorine. There's also a rule in skeletal structures that if you have a hydrogen on something other than carbon, you must draw it. So if there was a hydrogen, no, there can't really be, but if there was a hydrogen on that chlorine, we'll see it more often with oxygen or nitrogen, then I have to draw it. I have to say NH or NH2 or NH3 if I have it. I can't just write N and assume that people can figure it out, because it turns out you can do chemistry that might alter the number of hydrogens that are on there. So if we were trying to just look at this and figure out a chemical formula, we'd still count unlabeled endpoints for our carbons. We'd go 1, 2, and we'd say, oh good, I've got carbon. Then in general, when we're trying to find formulas of organic compounds, we generally go CHON and then other elements. Okay, so CHON are usually in that order. The elements we pick first, and then we pick other elements after that. And the order depends on a bunch of things, but we're not going to go into much detail on that. I don't really care with the order after that. So we're going to C, that's going to be 2. Hydrogens, let's count our hydrogens. I'll use a different color. We've got 3 here, we've got 2 here. Why? Because we've got 1 bond drawn, 2 bonds drawn, which means there are 2 undrawn bonds. There's never going to find a surprise hydrogen on a chlorine or on an oxygen or a nitrogen, because if there was a hydrogen there, someone would tell you. And so I'm not going to count any hydrogens there. So I just get 3 plus 2 is 5. C2H5, I don't have any O, I don't have any N, but I do have a Cl. So this is C2H5Cl. All right, another one. Let's draw... Oh, no, let's just do this. Okay, so we're getting a little more complicated here. Same rules. What do I have? I have a double bond over here, so that's just a carbon-carbon double bond. That's how you show it on a skeletal structure. Over here, I've got an end that's no longer carbon. It's an OH, right? Notice how I've got the H there, and so I'm specifically saying it. How are we going to do it? We're going to do CHON, and then we're going to do any other elements that we need to. Let's count our carbons. 1, 2, 3, and 4. Notice when I had this double bond here, I didn't double count the double bond, right? The end point means of, that whole thing, whether it's a single bond or a double bond or a triple bond. I don't count that as there's 2 on the side of the 3, there's 2 on the side of the 4, nothing like that. That's just 2 bonds between the same carbon. So I'm going to say this guy is C4. My next is H. I'm going to do my H's in purple. All right, what are we going to do? I got 3 here, 1 here. Why only 1 there? It's because there's 3 bonds already drawn. 1 here. Why? Because there's 3 bonds already drawn. 2 here, because there's 2 bonds already drawn. All right, so am I done? Do I say 3 plus 1 plus 1 plus 2? No. When I've got those other things on there, that contain hydrogen. I need to count them as well. So I've actually got 3, 4, 5, 6. Oh, I should leave that there. 3, 4, 5, 6, 7, 8. So it's C4H8. Okay. Notice when I was counting the carbons, I didn't count this one here because as soon as I labeled that endpoint as an oxygen, it ceased being carbon and became oxygen. So C4H8, I've got one oxygen, and so I do that. All right, let's do that molecule. What is that molecule? Well, again, I'm going to count my carbons first. I'm going to go 1, 2, 3, 4, 5, 6. That's all. That oxygen sticking out there doesn't have any carbons, so this is going to be C6. H is next. How many? Well, if I look at this first one, let's do my H's in red. This first one is only going to have 1. Why? Because there's already 3 bonds drawn from that carbon. Same thing for this guy. 1, 1, 1, 2, 0. 0 on that number 6 carbon. Why? Because there's already 4 bonds drawn, right? So I don't have any room for any hydrogens there. So I've got 2, 3, 4, 5, 6, C6, H6, and then how many O's do I have? I just have 1. Even though it's a double bonded O, there's just 1 O there, so I've got C6H6O. Okay? Those other double bonds there, all they do is kind of reduce hydrogens. That's essentially all the double bonds do in terms of figuring out chemical formulas. C6H6O. We're going to do one more. There we go. So we've got this molecule here. Again, I encourage you to try this, pause it, see if you come up with the same thing I do. But we're not going to do a play pause it for this one. Carbons 1, 2, 3, 4, and 5. Not here, because those ones are labeled endpoints, so they're not carbons. C5H, what do we got? H3 here. I got to erase these green ones, they're going to confuse me. 3 here, 2 here. How many here? Right? None, because there's already 4. How many here? None, because there's already 4. How many here? 2 and 1. So 3, 4, 5, 6, 7, 8, C5H8. And then I've got 2 oxygens here, so it's going to be O2 and then Cl2. So C5H8, O2, Cl2, being able to get that formula from the skeletal structure. You're not going to have to go the other way because it turns out there's so many ways of making C5H8O2Cl2 that you could draw these things all day long. So I'm only going to have you go the way where you get the skeletal formula to the chemical formula. All right, and that is the end of this section. Thanks so much for listening, and have a great day.